and that you have been given a tour at our College of Engineering. Hopefully you enjoyed it. So I very appreciate my colleague Mohammed for this invitation. Thanks for giving this opportunity to share what we are doing under our geocomputing lab. So I'm the director of the lab, and also I wear the hat of the chair at the geomatics department. I'll start with, can we go to the next slide, please? Thank you. So I'll start with some data from IPCC, Intergovernmental Panel for Climate Change. So especially starting from the global surface temperature. Thank you. So going forward. Thank you. All right, good. All right, I have a control of slides. Looking at the data compared with the 1852, 1900, so this is the 50 years surface temperature data. Now we're looking at the 2011 to 2020. So the global surface temperatures has increased by 1.1 Celsius degree, which is dramatic. Now, the main driver, of course, we already heard from a couple of discussion, the greenhouse gases dominated by the carbon dioxide and methane, right? And if you look at the graph on the right, it's a concentration of the greenhouse gas. And, you know, if I can point out here, from 1970, as you can see, the surface temperature actually jumped quite a bit compared to the previous years, and coincide actually with the dramatic increase of the concentration of carbon dioxide and methane. So that is really give us a significant warning that we need to take care of it. And now I think we are in action. Our project actually is most interested in methane. Of course, it is a very powerful greenhouse gas, second most important greenhouse gas, and compared with the carbon dioxide, actually it has a better, more potent 25 to 34 times compared with the carbon dioxide higher. Which is significant. However, I'm going to quote the message from European Commissions in 2022. So it's controlling the methane is the cheapest and the fastest way to slow the global warming in the years ahead. So that's one of the reasons that we are very interested in this, using the actually some of the data from the IPCC. So same, I'm using a lot of the reference from that group. As you can see, this is the black line actually showing the observations from 1950 to until to this point here. So it's a kind of validate some of the models presented. So we have 4 different models. No matter which one you are using, the FAR, SAR, and TAR, and the AR4. So no matter which one you are using, as you can see that the projection, the forecasting for the methane in the future years are significant. So, so that's why we are interested in looking at this monster here. The sources, of course, from the IEEE, from their global methane tracker into 2023 report. This is the graph I directly use it on the slides. So the majority of the contribution for the total global methane emissions, 60%, are from our human activities. The term is anthropogenic methane sources that include, so if you see the color here, we have, of course, the biomass burning. Another major one is agriculture. Another source, which is our interest, is energy section. It includes the oil and the gas, natural gas, and coal, as well as the biofuel, this small portion here. So all of the together, 60%. The rest of it are from the natural gases from the natural environment. For instance, the wetland, as you see, this is the big jump here, as well as some other natural resources. Now, as you can tell, the agriculture in the anthropogenic methane sources is mainly from agriculture, but energy is the second biggest contributor. Before we jump to what we are trying to contribute in order to reduce the methane emission, I like to use this graph. This is a very nice graph to summarize the major measurement and estimation for methane emissions. It is from the national academies, as you can this is directly from their report. And the majority methods include top-down as well as the bottom-up. So top-down are primarily using, for instance, satellite platforms or airborne platforms, and they are usually used for the global or regional type of inventory capturing. And their scale, of course, the spatial scale is going to be very coarse because they are going to be looking at the regional and global areas. And the temporal scales is also very coarse, maybe from weeks to maybe annual observations. And the bottom-up ones are more fine scales, as you can see here, either from the individual sources or to maybe facility to site. So those are on the either ground-based site, the measurement, or from the high-resolution, low flight altitude, the airplanes. So those are very fine detail resolution in terms of spatial as well as the temporal. They could be like monitoring the data from hours from the emission. So very different approach, but there is no very distinct differences between those two. Sometimes they're gonna mixed in terms of the spatial and temporal scales. So I'm gonna talk a little bit. Oops, I think I jump to the. Okay, a little bit about the top-down. So as I mentioned about the platform, so it's not just to measure the atmospheric methane concentrations, it's also going to model those to simulate the transport from emitter to observation locations like satellite as well as airborne. So the goal is to develop this inventory globally or regionally. And examples, I think this is the old version of it. I put some of the satellite examples here from the update, I believe. I think this is the old version. Oops. Did I do something? I just updated on the Google Drive. Do you want me to open that? Can you open it on the Google Drive? I'm still learning how to use the Google Drive to play the PowerPoint. Yes, it does. Which one? I think of the first one on the left. This one? Yes, that would be great. If you goes to the slide 6. This one. Yes, that's the correct PPT. All right. Do you want me to? Okay, I can forward. There you go. Thank you so much. I think those are good examples to show what are those top-down methods from the satellite. I put the satellite examples, GoSat. I think some of you use it. MethaneSat. So the resolution is going to be, spatial resolution will be from maybe the meters to kilometers. So that is a spatial resolution. And of course, airborne, there's a famous one, I think the next generation airborne visible or infrared imaging spectrometer. And it's used by the LASA mission recently to map the geological methane seeps in Alaska. And that's another example for top-down. Top-down approaches, they have plus and minus like any other approach. The problem is that because they are collecting those methane emissions from the atmospheric conditions, so they're going to include emissions from all the sources. It's hard to, isolate those emissions for specific sources you are looking for. So that's the problems. Of course, its strength is that if that's the goal to collect all the emissions, like for inventory purpose, this is the perfect approach to do so. For the bottom up, it's measure the emissions or model the emissions at a scale of individual emitters. So examples of those, I include a couple of ground-based network. So as you can see here, it's a total. The first one is from I think it's a TCCON. It's an international collaborative network that utilizes the near-infrared solar spectrometer to measure the atmospheric methane concentration. And you can also look at the other examples. So all of those are ground-based. So they can be very precise and very frequent and on those individual sources for methane emission, if that's the goal. That's the pros. Of course, the problem is that the minus part for this type of approach is that it's going to be very sparse. They only measure those locations, those emissions surrounded it, and it's going to be costly if you want to densify. So that's the problem. But that is actually the approach we like to rely on and expand on that, because we are interested in the very fine scale for our problems. So what we are looking for very high resolution remote sensing in order to monitoring the methane emitter we're interested. So just to give you a sense of this, what do we talk about, the very high resolution or VHR in some of the studies. It could be in terms of spatial or in terms of the temporary. So I'm using those three images as a spatial high resolution comparison. The first one is from the Landsat, which we all familiar with it. The spatial resolution is 30 meters. And the middle one is from SPOT. It's also satellite-based data, and it's 20 meters. And the last one is from the IRS, is 5 meters. So if you look at the same object on the ground, and if we are interested in image the very small scale, not small, high resolution object on the ground, so we definitely gonna increase our spatial resolution to at least we have the spatial the pixels represent minimal at that spatial the size of the object you are looking for. Otherwise, you're going to get a lot of post-processing problems. For instance, the one pixel may have information reflected by surroundings, so you have mixed pixel problems to process. So it's going to add a lot of a challenge in the post-processing afterwards. So what we are talking about, so why we're interested in the high spatial resolution. So this is the problems actually we are investing a lot of effort for the years to come also. So this is in Alaska, not in Alaska, if you look at the entire United States, we have a lot of wells actually drilled during the 150 years of oil and gas production, those period. And those wells are not used anymore. So we are abandoned, or we call them orphaned because they are not managed or monitored, not used. But some of those not properly sealed. So according to EPA, out of those, a little bit about more than 3 million abandoned wells, they are 2.15 million are not properly sealed or adequately sealed. And those, I just show you 2 examples. This is actually from the BLM. So this is actually properly sealed, and this is not. As you can tell that, visually they are very small object. Maybe the diameter is maybe about 15 to 20 centimeters, very small on the ground. The problem for those is that those uncapped or incorrectly plaqued wells pose challenges and a threat to the public safety and the environmental risk over the time. And the reason is that because I think if you look at some of the report in Alaska, we have very popular winter spot, ATV to running in the winter, where we, don't have the road system. So some of the report actually reported the accident caused by the debris or those, abandoned wells. So that is one of those kind of safety issues. And another thing we're curious about, are they still emitting those methanes? That's the question, because those, even though individual wells may not emit a lot of methanes, but together they contribute a lot of portion into the entire, methane emissions. So that is why we are very interested to, monitoring and identify those wells. But the problem is that challenges that those wells in Alaska, those time when the oil and gas production, those wells actually were from 1950s to 1970s, which were very old. And they are abandoned, and nobody actually monitoring it, even BLM. And some of them may be already buried by those vegetations growing on those. And some of them maybe just they are already below the surface. So how we're able to find it, you might say, well, why don't you look at the database? Yes, we do have the database, recording those locations, but they are not correct because if you think about the surveying system back in 1950 and 70, we are using the PLSS, which is public land survey system. So using those grade, and which is very coarse to identify those locations. And after some during the transition to convert those database to the current model, and people are just using a estimation for those locations. So you will see the net and long for those well locations, but they're not correct. So there's actually this is one location near I think it's near the Seward Highway to the east side of Alaska, and we use the coordinates from the database. Actually, we are looking for the abandoned well, which is the Eureka 2. That's the name of the well, but we couldn't find it. And there's no indication on the ground that this is the is the well location. So, so that is kind of a verification that those locations are not reliable. So we need to actually monitor those or to find out those and record those accurate locations. Now, another problem is that even this one here is actually has the pipe actually going out of the ground, and it is the correct location for this abandoned well. But because we don't monitor if there's a methane out of it, as you see, there's a hole on the pipe here. So it's good that we have some methodology to monitor regularly for those wells, so that we can make the informed action to reduce those risks. So, oops. So what are the current methods actually available for this type of method? Of course, airborne magnetic surveys, which use the magnetometers to detect anomalies in the Earth's magnetic field. So this is a very popular used by like Pennsylvania state. They are using this methodology to find out to detect those abandoned well locations and monitoring if they are, have that methane emission situation there. The strengths of those approach, of course, they are non-invasive, and also, we can get the data very effectively using the airborne platform, and it's very promising when we actually detect those vertical wells with steel casing. As you can see from this image here, this is from the work St. Vincent, etc. So they identify those abandoned wells by using this approach, because those vertical wells will show this as a monopole, that type of anomalies, compared with other metal object, for instance, like a metal roof, the building with a metal roof, and so on. So they're going to be bipole. So it's different patterns, so they can use it. They can even detect those wells, if they have no above ground evidence. So it's very promising in that aspect. However, because they are using the airborne and they have to fly, a little bit higher than the ground, much higher than the ground, of course. So they have limited spatial resolution. That may not be able to find out those small objects we mentioned about. And also it's going to be very high cost as airborne, type of missions. You have to consider the rental, the airplanes, and so on, all those logistic costs. So it's very costly. It's not effective for some of those old wells without those metal casing, or those casing has been removed. Some of them actually using the wooden ones, and this approach cannot detect those wells. So that's the problem for this method. Some other remote sensing method using the visible or infrared, the spectrometer. So because methane in the atmosphere, when those, in those spectrums, they have different absorption capability compared with others. So that could be used for image processing. The strengths of those type of approach, non-invasive, because the remote sensing approach, and economically it's cheaper, especially if we are having those spectrometer on the satellite platform. So we could collect the images very effectively, and it could include the emissions from all the sources, if that's the purpose you are collecting. Limitations are spatial resolution going to be very coarse, even airborne, so they cannot go to, as we required, up to the centimeters. They cannot. And the images collected, there are a lot of intensive post-processing requirements in order to identify those emitters. Of course, because they collect all the emissions from all sources, so it's very difficult to attribute the emission to the specific source, if that's a goal. So what we are involved in this work, we're using the F-score R2 project, which is the collaborative project with the University of Montana. Under this approach, this is a multi-year project. Under this project, we focus on the 3 research areas. The one is focused on the snow water resources. So this is actually to develop methods to estimate the water resources from the snow mountains. Actually, it's used for assessment and forecasting regarding that type of water sources. Another research area in this project is to develop method for better understanding of the fire activities, especially those wildfire activities, to provide recommendations for fire management and as well as related science, for instance, forecasting. Our group is focused on the abandoned oil and gas well detection. So that is what we're planning to develop in those 2 areas. First one is to advance the methane monitoring technologies. So as we go over some of those methods already, so we are focused on the drone-based methane survey. So we already purchased a couple of DJI M300, and we are going to use a very high sensitive methane detector on board and connected with a microcomputer, if you will, on board so that we can collect the data, recording the locations, and we can use that as our post-processing. So the methane sensor on board is very sensitive. So we're going to test it if we have, because the emission from those abandoned wells are fugitive, right? And it's very sparse. So we're going to do some simulation on the ground to have a manual release from the methane, and we're going to fly the drones around those test areas and see if we can detect it. So that is going to be happen this summer, and we'll use that result to actually doing the field work for the 4 unknown, actually 4 wells, abandoned wells near Anchorage, which is 2 in, I think 2 in Houston. If you go a little bit further than Palmer, and there's 4 abandoned wells, and the other 2 are going to be the 2 we visited last year. So we're going to see if we can identify the actual locations, or if those wells are emitting the methane. So that is what we plan to do in the next 2 years. And then the other approach is other aspect in this project. We're going to advance the technologies in VHR object detections. As we mentioned, those wells, if they don't have the methane emission, right? So we are going to use some of those indicators, for instance, from the LiDAR data. So we're going to collect a very high resolution LiDAR data. And there are some of the revised terrain in those wells, and maybe there's some debris from before, like abandoned, maybe some other object on the ground, or they have the trails to those locations. So all those kind of indicators that we're going to combine together in order to identify those small objects on the ground. The very promising approach we have tested so far is based on the machine learning, and one of those areas from machine learning is the CNN model we're trying to develop. So convolutional network, a neural network. So that is, we can combine all those indicators together. So in order to detect those objects. And the technology we develop from the VHR object detection is that we are planning so they are going to be very extendable to other problems. For instance, we can use those same technology to monitoring the after natural disasters for those buildings, how many of them are damaged, the levels of damages, so we can collect those data using the drone-based images. So that's we can extend our approach to other applications. But for this project, our goal is that we aim to provide those updated and accurate abandoned well locations for improved mitigation, site reclamation, and hazard removal. And that will be a very informative data to provide it. So for the better decision making in order for those sites. So that is we're still working on. So if we have a chance next time, I'm gonna have more reports regarding those tasks we have down there. But for now, I think I'm going to stop here, and I'm happy to answer any of the questions or your comments. Thank you.
Okay, you go ahead.
On the slide that you had, the energy bar on with coal, oil, and natural gas, you call that a methane source. But if the fuel is burned, it's going to be a CO2 source, not a methane source.
This one is only focused on the methane source.
Pardon?
So this one is only focused on the methane concentration. So those are sources. So definitely they have other.
They have methane in it. Methane's going to burn. It's going to combust and make CO2.
The methane associated with taking the oil out of the ground, and so on, and escaping from pipelines and so on.
Our methane doesn't escape from our pipeline in Alaska.
Okay.
Well, I admit. I have to admit, I'm not an expert in those area, but this is definitely a direct copy from the IPCC, from IEEE, from the report. So that is one of the source contributing to the methane emission.
Spent a lot of time monitoring for methane gas inside the facilities that we've got. So we're not leaking methane, and when we flare it, it's going to burn it. So.
But I don't think every country is as diligent in that process. Yeah, but she was giving us the global numbers, so the IEA only does global in that, I assume.
Speaking of global methane emissions and oil wells and leaky pipes, you got a satellite that can detect, then we can detect who the worst offenders are, right? But then what if they're run by authoritarian regimes that decide, you can't make us, we're not going to do anything? And I'm not going to mention any names, but I think we all know who they are. So what do we do in that case? And that right there is a conundrum that, you know, a lot of us have, is like, well, what we do in the West is one thing, but the West is actually a small piece of the puzzle overall. And so what happens when Russia doesn't want to do something, or when other countries don't want to do something because they don't want to regulate it? Then, you know, I mean, has that been discussed?
Oh, I think this is a little beyond my perspective in this project. So the data I'm quoting from IPCC as well as from IEA. So those are just to give the background of the methane sensor. Actually, methane emissions is one of the actual critical tasks we're trying to mitigate. And my purpose for this presentation is that using those as my background regarding the project we are trying to do. So if beyond that, I'm not expert, I have to agree that with that.
Yeah.
Hi, you mentioned the pros and cons of certain types of meters. I was wondering if there's any effort to cross-reference the different types of meter measurements that are being taken.
Yeah, definitely there are hybrid approach that in consider top down or bottom up, so that they can get the emissions as they plan to do. Yes.
that 3 million number, that you mentioned, where, can you let us know, like, where that comes from, and, is that a global number, or just Alaska, or the United
It's
States?
from the EPA, the Environmental Protection Agency, and it's definitely going to be global, United States, entire US.
Yeah. And I just looked up the Canadian, it's about 400,000. And there's a big effort in capping abandoned oil wells in Alberta.
Mhm.
It's a lot of investment by the province to do that.
Yep.
So this is it's an interesting issue. The question is, what is the program, like the programs in different countries to follow up
Mhm.
on the action? But I think the first thing people need to know is where is the methane escaping. So I think what you're doing is number one.
Yeah, microsite.
The trial that you're doing with the drones, what altitude are you going to fly them? How sensitive are your sensors?
Yeah, the drones from what we have down, I think it's better to be around like 10 to 15 meters high. If it's too high, so the sensor cannot detect it, we're gonna see what's the optimal height for our test. The sensor is very sensitive. I don't remember the actual parameters.